I've got a bit of an echo going. Not from my. Might be your phone, I think. Yeah. Yeah, so yeah, we've got Newcastle on Hunting on Newcastle on time. Very different place and a lot further away. I like to say that as well because my house is, as I pointed out a few times to people, my house is about to be somewhere. So it's kind of a nice place. But, yeah, a long way away. So let me just go back quickly to my title. So there's a couple of keywords in there. As Bill mentioned, the first one is neutron. Neutron and segment range. So let's start before I talk about those. So neutron transmission. First of all, the sort of 2-minute introduction to neutrons. So sort of scattering basics, if you like. So the neutrons essentially going to interact with three neutrons. They really interact with the balance. So the electron cloud is essentially they're interacting with all the electrons. So you get it from the nucleus, and that generally means one is they penetrate quite a long way in matter. A lot of the times they lose a long way through some materials, and there's not very many most of the space not made up of the nucleus. So there's a lot of extra space. And the other thing is that their attenuation is kind of not really related to the mass. So for X-rays, they're carrying electrons. So the more electrons, the more they scatter. Whereas neutrons, it's a bit more complicated. And there's the scattering from the nuclear around the nuclear around the kind of what's the point of going on there. So the way they do that is pretty hard. And what that means is that the actual attenuation rate of neutrons is kind of very different to X-rays. So these two graphs, these are pinched off the website of Grenoble. This is X-rays at the bottom, and you can see as you go up in the atomic number, you get more and more attenuated. Top graph or the top picture is neutrons. A couple of key points to look at. Hydrogen is really attenuating. So hydrogen has quite a big neutron cross section. Boron is huge as well. The boron is used in a lot of shielding. Most shielding for neutrons is plastics. So lots of hydrogen doped with boron. So if you want to stop neutrons dead, you just get a sheet of plastic with boron in it. Other things on here which are kind of interesting is that aluminium is almost transparent. They build windows to let neutrons through despite the sheet of aluminium, whatever is lying down, like pressure or gas, whatever, and it just goes straight to the aluminium. It's not even there. Steel is sort of in the middle, right? So we're going to do good measurements of steel to penetrate a long way in steel centimeters. And so you can do all the same sort of things with neutrons as you can with X-rays, so diffraction and imaging and the like. Because of this situation with attenuation, you get very different contrasts between neutron images and transmission images and X-rays. And there's this famous picture from PSI, somebody's camera in the beam, in an X-ray on the right-hand side, and then neutron beam on the left-hand side. In certain X-rays, every bit of metal in the camera is dark because it's whereas on the neutron side of things, every bit of plastic is dark because it's got lots of hydrogen inside. And the weird thing is you've had a neutron to the nucleus that is hearing something becomes transparent again. The key thing for us is that cold and somewhere between sort of cold but thermal neutrons have neutron weighting around 1 angstrom to 5 angstrom
so that's neutron basics. The second word in that title is strain. This is key. So we're doing mechanics, neutrons, and neutrons are really useful for that. In particular, we're interested in residual strain, which is essentially kind of locked in stress getting components due to how they make. So if you bend it with the metal or something, part of the collapse behavior, then there's actually the locked in strain that object that when you let it go, it'll be happy in the equilibrium, but inside the war going on, some parts of the tension, some parts of the compression fighting each other. And obviously you need to know that to make the components going into the earth and you know what's going on inside, you know what loads you can take or how it's going to behave. And this is oh, that's chopped off the bottom of my slide. Not sure why that happened, but yeah, it's sort of important, I guess, for a lot of you additive manufacturing processes. So the components to the vessel is essentially want to be well, the whole thing is well through this process, and will have used to this extent through the space. So it's sort of an important kind of consideration in all of those kind of new sort of additive manufacturing processes. Okay, so to link the two together, I mentioned before that the wavelengths of neutrons are similar to the lattice spacing. So that means coherent scattering is a lot about structural materials. It gives the little cartoon version of diffraction from the crystal, where you've got an incoming beam, and sort of drawn again here in a sort of cartoon of the crystal. Incoming beam, and obviously this will transmit through. And if you have a direction where the extra kind of length through the, this sort of angle change, the extra length is one whole wavelength, and you'll get structural interference and you're more likely to scatter if you follow in that direction. And that, this is a simple sort of 2D case, you can kind of see the obvious that that's related by drag law, which 10 times later is 2D sine theta. And so essentially, that scattering angle or wavelength, or the way to do it, tells you about what happens. So there's sort of two main approaches. You can either fix the wavelength, through a monochromator or something, and measure the angle of the diffraction head, and that will tell you the lattice space. Or the alternative is fix the angle, and you measure the wavelength to get scattered, and that will also tell you the same thing. So, two sort of divide neutron scattering. Here is continuous forms like reactors. They're predominantly the first approach. Second approach is pulse forms, which are the same moment for time of flight measurements and the like. Either way, essentially, we're measuring lattice spacing. So that's really what diffraction is all about, measuring lattice spacing at the level. And from our point of view of being in strain, any strain that you see in an object is going to change lattice spacing. It's quite straightforward. You just measure a relative change in that spacing, C minus C naught on C naught, and that will come up strain. And in particular, that's telling us the strain in terms of how it changed the spacing of that lattice. It essentially is just a component of strain that's normal, normal for lattice function. So essentially, through different approaches, we pick out one component of strain at a time. The normal component in this kind of measurement direction, which is the sort of bisecting, the angle that bisects the sort of incoming and diffracted beam. And so, there's a whole host of kind of traditional techniques around how to do that kind of movement, how to kind of measure the strain and the like from that. We're doing something slightly different. We're using the same kind of ideas, but we're doing it in a slightly different way. It's a pulse source. So we're talking about sort of transmission imaging or energy resolved imaging here. So it's a pulse source. So we're doing the sort of second of these options. So we fix the angle. We measure wavelength to figure out what's happening with lattice planes. But we're doing it in the direction that is, well, 180 degrees from the incoming. So in other words, we're looking at the backscattered radiation that happens for a sample. And now I'll just quickly introduce time of flight measurements. So at a pulse source, the beam that you actually generate comes from neutron pulse. So there was installation processes from other stuff, and essentially, several times a second, many times a second, you'll have a pulse neutron generated, and they will start at the same time and the same place. It's a very short pulse, milliseconds. Very short pulse created at one point, and you can read it a long way down the sky, a lot further from that, and obviously the wavelength of the neutron is related to their momentum. Okay, it's with me. I'll carry it with me. So the wavelength of the neutrons is related to their momentum, and so the faster they go, the lower their wavelength. And so if you just wait for a while, if you let them travel through a certain distance, the ones that get there first have got the shortest wavelength. The ones that get there last have got the longest wavelength. So you just time the detection, and that tells you exactly what the wavelength of that neutron was. And so what that means is that you can measure, spectra just by measuring time of flight. And in imaging, that's done in this sort of transmission direction. So we have a source, we have a long guide, we put a sample in front of a detector, and the detector, just like a normal sort of X-ray, just measures what hits the detector, but it also measures what time it arrives at. And from that, you can kind of measure a spectra. So as a function of the neutron wavelength that you saw, you can kind of measure a transmission rate. So if you imagine a measurement like this, it's kind of like a normal radiograph, but behind every single pixel in the radiograph is full spectrum of wavelengths that you detected. In those spectra, we get these features called Bragg edges. And maybe I should draw a quick picture of where they come from. So if we have a crystal, just one crystal, let me draw. Which way should I draw? Let's go this way. We have crystal, and we've got lattice planes in there. It's obviously much more complicated than that. There's lots of lattice planes. But it's got a set of lattice planes. We've got a beam that goes through, and that set of lattice planes will diffract radiation if two things are satisfied. The first thing is Bragg's law is satisfied, so n lambda is d sine theta, and the second one is the geometry is right. And so what that means is somewhere there'll be a lattice plane, a normal. We'll get some sort of geometry where this works, and this will kick off a certain wavelength that will be kind of scattered in some direction. And if you like, what's found at the end of this is, well, what we started with minus anything that got scattered by this crystal. So what that means is, in terms of transmission rate, so I on I naught. Okay, so there's a kind of dependence on wavelength. So really short wavelengths have got lots of energy, they'll go a long way through. Long wavelengths are the opposite, so there's sort of a general way of this anyway. And what happens here, if we've got this crystal that kind of picked off these wavelengths, is that we'll take a chunk out. It'll be a bit missing, right? And I'm not telling the whole story here. There's actually lots of these sort of chunks that are missing from all the different lattice planes and whatnot. But regardless, we've got a little piece missing. And if I put now a series of crystals in the wavy beam, and these have all got different angles, different lattice planes in all the different directions. And essentially, we just start taking more and more of these chunks out, right? And so essentially, we've kind of reduced this beam, right? We've sort of removed all of this coherent radiation. But the point is, the best we can do in terms of this geometry is backwards, right? And that happens from a crystal that's got lattice planes that are already perpendicular to our incoming radiation. And these lattice planes will scatter directly backwards, right? The sort of scattered radiation is sort of going back towards the source. And we can't do any better than that, right? Once you've already gone backwards, there's no other geometry that will be allowed. And so this wavelength, whatever this is the last point in the graph where we can scatter radiation for that set of lattice plane. And so what that means is we have a jump, right? We pick a point in that wavelength, and nothing past that wavelength can get scattered by that set of crystals. And so that happens through all the different various lattice planes that are in a crystal. And so this kind of transmission measurement, what you see is this set of steps, and every step relates to a different set of lattice planes inside the crystal. From our point of view, that's interesting because the position of that edge is related to a lattice spacing, right? So, lambda equals 2D, and so we can just measure where that edge is, and any movement in that edge will tell us what the strain is in that direction. Right, so we're measuring strain in that kind of forward direction or backwards direction. It's the same, right? And so we can make an image of strain, right? So behind every pixel now is a strain measurement or a strain calculation, and that strain calculation is what's happening in that forward direction. And people have been doing this for kind of 10 or 15 years now, doing this kind of measurement. Key point is that strain is measured in that direction of the beam. All right, so I've just illustrated two different sort of vague kind of techniques. That it's kind of the traditional one that's existed for a really long time, where we can kind of pick off a little volume inside the sample, and we can kind of probe what's actually happening in time in terms of strain at that point. That's sort of diffraction for the model. The transmission model that we're talking about now is sort of similar, except we're doing an average along array. We're not picking a single point. We're doing an average along array, and we're measuring strain in that direction, in that transmission direction. So keep that in mind as we sort of go through the rest of this presentation. This is the one, I should say, this is the one we're interested in, right? This transmission one. And the point is, okay, the other technique, diffraction, we can just probe points. We can measure whatever we want, and each measurement will tell us what its strain is at that particular point. In the transmission model, we get kind of blurred along the line, and so we sort of see a tomography problem, right? There's a natural tomography problem here. And so the question we have is, can we go from a set of these kind of images of an object backwards to working out what the actual strain field is inside an object? And that's been a problem we've been working on for a little while now. Okay, so what's the transform? It's as we've probably seen in a few different talks so far in the program. It's a longitudinal ray transform. So we're going from a tensor, in our case, a rank 2 tensor field, and we're sort of looking at a component of that back to a scalar. So we're doing a scalar measurement of the tensor field along rays. The component we're looking at is the component in the direction of, the normal component in the direction of that ray that we're passing through. Okay, I've written it sort of slightly different to what sort of appears most of the time in sort of mathematics in here, as in I've done this integral only over the domain of our the thing we're trying to reconstruct. So we haven't extended off to infinity, well, because we're engineers and it's easier not to, right? The other point is that it's an average, not a sum, if you like. So the measurement we're doing is an average over that ray, the portion of the ray that went through our object. So we have to keep track of that as well. Okay, so keep in mind we're doing a scalar measurement of a tensor field, so this ends up being inherently ill-posed. And this is sort of pointed out by Bill's friend. I've never met him, but Bill's friend in Sharafudanov in Russia, who's got this this book on integral geometry of tensor fields that it's got this wonderful preface that talks about well, it's Russian optimism, right? It's essentially a preface that says no one's going to read this book. Why would they ever bother? It's too complicated for anyone in applied maths, and it's too boring for anyone in anyone who's too complicated for an engineer and too boring for an applied mathematician. And in any case, both of them are not going to admire my Russian English. And it's it's not true. It's actually quite a well-written book. And it's got this theorem buried in the middle of it, talking about how essentially how this problem is ill-posed, and essentially the null space is anything that is anything that can be written as a derivative of the potential. And this kind of sat there for a while. It's not exactly a brand new book. The field's been kind of going for, well, probably the whole time people have been trying to solve this problem. This book has existed, and I don't think anybody realised until Bill published this paper with Phil Withers that kind of. I think what you did, Bill, was you basically said it in a way that engineers could understand, and everyone went, "Of course, this is not going to work." So said another way for the engineers in the room. Essentially, the measurement we're doing is the average of normal strain along the line that passes through our object. And, it's not exactly rocket science. That's just the relative change in the length of that line, right? So if you average strain along that line, all you've done is you've said, well, what's the length of that line, L naught? What did it change to? Let's divide by L naught, right? So all we've done is we've looked at the length of that line. And the problem is, I can then imagine that object fixing the boundary and rearranging the stuff inside, creating any strain field I want inside. As long as I don't move the boundary, I'll measure zero. So essentially anything from that, that set can be added to any solution, and we will never see it, right? And the nice thing is for explaining this to engineers is that these are real, right? These actually exist. For example, if I just take a plate, two-dimensional plate, and I turn gravity on and pull the plate down with gravity, I get tension at the top and compression at the bottom, and I get some kind of weird, other stuff going on because of Poisson strains. And the point is, if I do any projection through that strain field, I can't see that, right? So how do I know that that's not there in my solution? It's kind of obvious to people in this room, but it took engineers a bit of time to see that, and thankfully Bill pointed it out. So the bit that's cut off the bottom there is I guess where we stepped in here, or maybe where we kind of saw we could do something. And the point is that, okay, it's ill-posed from the point of mathematics, but obviously if we start bringing physics into the problem, we might be able to actually fix that. We might be able to pin the solution down through other constraints from the physics of the system. And so that's what we kind of did. The first case was the simplest version of that, which is to say, well, hang on a minute, what if there are no kind of eigenstrains, people call them? What if there is no residual stress going on? What if it's just a pristine object that somebody's putting forces on? And if somebody's doing that, then essentially the strain that is inside that object is going to relate directly to the motion of the boundary. And so from the point of view, we do have the derivative of a potential field. So why don't we just look at what the boundary does, and then we can work out what's going on from the point of just linear elasticity theory. And so we went down this path. Essentially, the idea is, we do these ray measurements through an object. Each ray tells us a relative, change in, motion of the boundary, and essentially we reconstruct that, and then we can take that set of motions on the boundary and we can put them into a finite element model or something like that to work out what the strain is inside that object. So the super rough kind of numerical approach to that is to essentially just discretize the boundary. We don't care what's going on inside. And the boundary is discretized, kind of, as a set of points, and between the points, we can put shape functions in or whatever you like. And essentially, each ray is a measurement of, if this boundary displacement is phi, each ray is just a, phi out minus phi in, dot product with the unit vector that, in the direction of the ray. And essentially, we just assemble a huge system of equations from that and solve them using least squares. And the interesting thing is that set of equations is always ill-posed, and the dimension of the null space is always 3 in this particular 2D case because we can't see rigid body motions. So it can move in 3 different ways that we won't see anything in our measurement. 6 obviously if it's in 3D, and the 6-dimensional version, sorry, the 3-dimensional version, we did see 6 in terms of that dimension. But nonetheless, you can solve this in lots of different ways, just as an L2 minimization or something, and get solutions. So we went and did this. We did this in simulation, and then we got some beam time and we gave it a go. So this is the first experiment. And the first experiment was a little piece of steel in the shape of a C. And we put load on that just to kind of crush the C a little bit. Obviously elastic loads, because we don't want residual stress at all. And on the Raden instrument in J-Park in Japan, we measured a whole set of these profiles. It's sort of 2-dimensional experiment. So it's sort of averaged along the length of the sample. And we measure a whole heap of these sort of profiles of, essentially like that movie I was showing before. And from, I think we were 86 projections, and from those 86 projections, we assembled enough information to solve where we got 47 boundary nodes, so just 47 nodes around the surface, and throw that into a finite element model and solve, and we got pretty good results, right? So there's 3 sets of graphs there. The top one is the sort of reconstructed version from this process. The middle one's a finite element model of a really simple loading, right? There's nothing complicated about the loading. So it's a finite element model of the same system. And the bottom set of graphs is digital image correlation. So we can actually do this optically, looking at a speckle pattern. And it's pretty good, right? So we were sort of all happy that that was working. You can look deeper using the traditional approach, so this is the sort of diffraction approach where we kind of probe individual points. So we just go around looking at individual parts of the sample and measuring what strain there is. And that's the set of measurements that we did using the Quarry instrument in Australia, the one we have access to in our neutron source in Australia. And doing the right kind of thing that's not perfect, right? And in particular, high strain gradients, we didn't see, we saw a few sort of issues, but largely speaking, it was pretty good. So we were kind of happy with that. And so we went back to thinking about the actual bigger problem, which is residual stress, right? So the situation of residual stress where essentially the total strain that's in an object, which is compatible, which you can do integrations of and work out displacements, is made up of 2 parts. One is the elastic strain, so what strain is in that object that's related to stress, if you like, through Hooke's law, plus what have you done to that object that's not recoverable, so from plasticity or from some sort of thermal process. And the point is, each of those 2 are not compatible by themselves, and so we only see this one. I should say that's very important to recognise. We only see the elastic strain. So if we've got a plasticity in metals, is usually due to kind of just moving the lattice over one atom through lots of different mechanisms. They don't change, the plasticity doesn't change the lattice spacing. Right? What we see is only the elastic part of strain that's related to the stress that we're applying.
Chris, like sliding,
Yeah, exactly. That's exactly what's going on. The planes just slide; they don't get further apart from plasticity. And so we measure this one, right, which is inherently incompatible. So it's not related to boundary displacement. So we can't do that same trick. So we need a better approach or a different approach. And essentially, the approach we're using is still more or less the same thing. We just apply a constraint, like essentially the finite element model in the other approach was just doing that. It's just applying equilibrium as a sort of known physical thing to the system. Well, we can just do that to our system, right? Except now we just need to do it at every point where we know it has to satisfy the equilibrium equation. So every single point in our domain has to satisfy this equilibrium equation. If you work in 2D, you can write that in sort of simpler versions. So C there is the sort of the elastic tensor, if you like, so Hooke's law. And the question is, how do we do that? We've essentially done that in two different ways so far. The first way that we did it was essentially just through sort of a least squares fitting of Fourier series, where that constraint from equilibrium really just gives us another constraint on the Fourier coefficient. So it's kind of a LSQ Lin type problem where you've got sort of a least squares optimization for the measurements, and it has to be constrained by equilibrium. So I'll show you some sort of results from that. I should say the results from these two versions are basically indistinguishable in terms of how they performed, which was kind of nice. The second version, I had a very good postgraduate student that came from kind of machine learning mechatronics background who essentially brought along with him Gaussian process regression, and that ended up being quite powerful in this approach, where we essentially satisfy equilibrium by things called Airy stress functions or Trami stress functions, which I'll talk about in a moment. But essentially, Gaussian process regression is it's an inference technique based on sort of the Bayesian approach, and we can kind of constrain it a little bit to the sort of the super high level overview of what's going on. So in general, we want to work out a function at some point, and we assume that function is a member of a Gaussian distribution, and that there's an assumed covariance function where where we can relate 2 points in the domain through that covariance function, depending on how far apart they are. And there's a couple of parameters in there that kind of let us control that. And we go away and make some observations, and the observations are based on some kind of linear operator that's acting on that function. In our case, they're line integrals, which are just another linear operator. And we can kind of form, or the thing we're trying to work out, and those observations are jointly Gaussian of the form that's sort of written there, where all those kind of different parts of that kind of covariance matrix we can kind of build up through kind of what that kernel function looks like. And so essentially, you just build this for all the different observations that you made, and then you can make a posterior estimate of what the function should do, right? So what the function should be at that point. So as I say, that's the kind of high level kind of idea about what that is. How do we apply that to strain? Well, we want to work out strain at a point in our domain so that it satisfies equilibrium. And the way we can satisfy equilibrium is we can define the stress through a thing called an Airy stress function, which is it's just a potential, and we define stress by derivatives of that potential in a way that automatically satisfy equilibrium. So this is 300-year-old result in kind of elasticity theory. And so putting that together with Hooke's law and kind of what we're doing here, we just have another operator in the way. So we have this potential field, and our final measurement, or our operator that does our measurement, it's just a combination of the ray transform and that operator that turns our potential into stress. And then we can just build a Gaussian process to estimate that potential. And in fact, we can do it that way, or the other version is you build that operator into the kernel function. Is the other kind of approach, but kind of equivalent.
So the area stress function kind of gives the entire kernel of the equilibrium equation?
I think in 2D that's true. I should be careful not to jump out of the bounds of things I shouldn't say, but I think in 2D that's true. There's three-dimensional versions of this as well, where you can, which I'll talk about in a moment, which are Beltrami stress functions, and they can be done as full tensor that covers the whole gamut, or you can kind of simplify it in different ways, and lots of people have. But I think in 2D that's true. Isotropic, yeah. Okay, so I'm just going to present a couple of examples of us doing this. Some measurements that we did sort of demonstrating this. This sort of experiment 2, if you like, which is looking at residual strain fields. And so we looked at 2 samples in this experiment, and it's a 2D experiment, so we can kind of stack the samples on top of each other and get 2 for the price of 1. So we're projecting and averaging anyway, so it doesn't matter. We just stack as many samples as you can in front of the detector. So the 2 samples we did in this experiment. The first one was a crushed ring. So like on the left-hand side there, just a little ring of steel that was kind of stress relieved, through a thermal process, and then we just squashed it. We just sort of squashed it on the diameter to build in residual stress through that plasticity. And the second sample is a ring and plug sample, which is something that people use all the time in this area as sort of standard. Our ring and plug is a bit different than normal because our plug is not in the middle of the ring. So we're looking for some kind of something that's not axisymmetric. So you get a piece of steel, you drill a very precise hole in the piece of steel, with very high tolerance, and then you make another piece of steel that out of the same piece of steel that is ever so slightly too big for the hole. Once again, surface ground and very precisely controlled dimensions. And then you put the big ring in the oven, and you put the little plug in liquid nitrogen, and you quickly put them together, and everything sort of becomes happy, and you've built in some stress, right? So the plug is too big for the hole that it's in, and that's a form of residual stress, right? Very different samples. The first one is like a distributed residual strain, or sort of eigenstrain, if you like, whereas in the second case it's localized to the interface between the two. But nonetheless, they're sort of, they're both samples that have got residual stress. So there's stuff going on even though there's no external loads applied. And so yeah, that's right. Yeah, and if you cross that boundary, then you've got exactly. So these 2 samples, there's just a radiograph on the right-hand side there of them stacked up on top of each other. And essentially we're doing a 2-dimensional experiment, so we just average along columns of pixels in those images. And we make sort of something which I suppose you could call a sinogram on the bottom right-hand corner there. So it's not really a sinogram, it's a strain sinogram. It's a projection of the strain tensor, but it kind of looks the same, right? And so obviously we're working on that transform to go back to the other to the strain field, and we see something like this. And as I say, the 2 different approaches make essentially the same pictures. There's not a lot of difference between them. So we've got 2 samples on the other side. In each case, on the left-hand side, we've got traditional measurements, so point-wise measurements where we go along with a diffraction instrument, and we put they call it a gauge volume. We put the sort of measurement volume on each of those dots and just measure what's happening, and then apply some kind of interpolation to draw the pretty colors. And then next to that is our reconstruction from that process. And you can see a lot of features that fit, right? I mean, certainly in the ring and plug sample, you can see the plug, you can see that it's in compression, you can see the kind of tensile sort of behavior of what's going on outside of that. So there's sort of normal in X, normal in Y, and then you've got shear in the middle. So things are behaving, right? They look roughly right. Details not so much, right? So in particular, some of the kind of features of this are similar to this, but they're much stronger, and they're kind of we've missed some of the stuff, right? Certainly around this sort of tensile behavior here, right? We don't quite see that quite so strongly. And certainly if you plot profiles, you see some of those errors. You see some of those errors kind of creep in, right? We're sort of drawing lines in our sample and drawing the measurements versus the reconstruction. You sort of see, the right kind of behavior, but not quite right. And so we thought about ways of, well, what's going on here. We spent some time trying to work out what's going on, and then eventually just worked out that, well, we've got quite a powerful tool to just squash it back to where it needs to be, right? Let's just apply more constraints to our system, because we know that our samples don't have loads applied to the outsides, right? We know what our boundary condition is on our samples, and to be honest, most residual stress measurements, that there's no loads applied to the outside, right? The samples are sitting there on a bench. So not if gravity is such a tiny force in comparison to what we can measure. I mean, the error bars are a good couple of orders of magnitude bigger than any stress that gravity will give you in these sort of situations. So largely speaking, there are no loads applied. It's only internal, this internal war that's going on. And so we can apply that as a constraint to our, in addition to our equilibrium equation, we have constraints that can come from boundary conditions. So ideally, on that boundary, we have no surface traction. And the first thing we did when we thought about this is to look at, well, how bad is it? And so we just looked at our reconstructions and sort of asked the question of, well, what stress is it actually telling us is on the boundary that shouldn't be there? And you can see that bottom graph is from our transmission data, and there's quite a lot, right? 250 odd megapascals, which is quite a lot of stress, is the kind of error on that boundary that shouldn't be there. And interestingly, we went back and looked at the diffraction data as well, the sort of the accepted kind of approach, and it had lots of stress that shouldn't be there on the boundary too, right? And I'm not saying that the measurements are wrong. I'm just saying that the interpolation that everybody does, and the first thing that happens when somebody measures a bunch of points like this is they interpolate the field out to the boundary, and you can't measure at the boundary. It's not possible to measure at the boundary. You get systematic errors if you do that. But certainly the extrapolation to the boundary, it's just being done by whatever algorithm you've chosen to extrapolate, and so it doesn't have to satisfy equilibrium, and it doesn't, right? No, there's. I'll do it quickly, but essentially, if you've got a boundary, if you put that gauge volume off the boundary, then essentially you're only getting a measurement from this bit of material, and you're measuring. In reality, you're measuring a very precise angle with this diffracted beam came off, and the shift from the center of that volume from here to here is enough to actually see a change in the measurement. And so you can't have a gauge volume that overlaps the boundary. It'll just give you an error. And so every measurement has to be at least this far from the boundary, right?
It seems like it's above that, right?
Yeah, and people have tried. Yeah, people have sort of tried it, but effectively they just don't go that close, right? So they just have, you're always in from the boundary somewhere. And the point is that the extrapolation will be wrong at that point, right? If you extrapolate to the boundary. And incidentally, we went down a whole path of using Gaussian process to, with equilibrium and these constraints to fix the kind of normal diffraction measurements too, right? So we have an approach where we can kind of put all those constraints on those kind of measurements as well. Anyway, so the point is we can fix this now in terms of the the reconstruction because we just pick a bunch of points on the boundary of that object and pretend we measured that the stress was zero there, right? Well, not stress, sorry. The surface traction was zero at those points, right? So essentially, we just impose this constraint at a set of points, and you can put as many as you want, just as extra kind of pretend measurements at that on that boundary, and you can kind of fix those problems. And when we did that, everything basically became much better. So you can sort of see a comparison there between just equilibrium and then with traction as well, with traction constraints. And with traction constraints, everything essentially matched up, and we were quite happy. All right, I'm running short on time a little bit, so I'll speed up. Last experiment, we did this in 3D. So much more complicated experiment. We can't average along columns of pixels anymore. We have to sort of do proper imaging where we can take an actual image. The sample in this case was a steel cube with a titanium plug. So just like our ring and plug sample, except we've now got a different material for the plug. Titanium is relatively transparent and has different Bragg edges to steel. So we can essentially ignore the fact that it's there, right? So essentially we've got a steel cube with with loads that are applied on the internal the internal surfaces of the hole. And we did three-dimensional tomography on this. So in other words, not single-axis tomography. We've now got to move in more than one axis. Here's a picture, right? So it's in a goniometer, and essentially we move that sample around and we probe. We take projections from a set of directions that are all around that sample with two movements as well. So one of them, some of that we can't see because we're going to go drive through motors. The beam will go through motors and stages and whatnot. So at some point, you have to flip the sample to do other directions. The reconstruction is basically the same idea, except instead of airy stress functions, we look at a kind of three-dimensional generalization of that, which is Beltrami stress functions. So once again, you define the stress in a way from a sort of potential that
I mean, it's easy in a way, right? Divergent, column by column divergent signal looks like divergent. So
you're constructing something that's divergent. Yeah, you're building something that's divergent, so that's just, yeah, that's right. Divergence is zero, right? Yeah. Anyway, so essentially the same approach. We just build that in and reconstruct the Beltrami stress functions, I should say, plural. And we get these measurements. So once again, we've got comparisons. The top one is our reconstruction, just on two different planes in the sample, compared to a finite element model. Once again, it's a very simple loading, so it's easy to get a finite element model to behave in this simple case. So we're making comparisons between those, and we also went off and did diffraction measurements, so probe individual points over one of the planes, and we can sort of see comparisons between those. So and in the top row, this is sort of the diffraction measurements, and we haven't interpolated. That's the actual size of the gauge volume, is shown there. And you might ask why we don't compare over the whole domain, and that is because to take that measurement, I think that that and another plane that we did was about 6 days of measurement on the diffraction instrument to measure over a plane. Whereas the nice thing about the tomography measurement is that we're getting that same information everywhere in the same time. And if you wanted to do every single point in the domain using the diffraction approach, there's 250 days of beam time, which nobody in the world is going to give you that. That's just not, it's not feasible. So, in 2D, it's about the same, right? We can sort of probe every point, or we can do tomography, and it'll kind of work out similar orders of magnitude of time to do that. But in 3D, there's just no comparison. So tomography will give you stuff way quicker, and much more information than will happen through diffraction. All right, so I think I might pull up there because I'm running out of time. I'll just finish up with sort of advantages and disadvantages of what we're doing. Probably the biggest advantage is 3D, in that we get a full, it's full field measurement. So we get every single point, and obviously equilibrium is guaranteed by the way we're reconstructing. The funny thing is the disadvantage is the same point, that it's a full field measurement. The power of the diffraction approach is that, if you just want to know what's happening at a point, you can do that measurement in seconds or minutes, right? Whereas we've got to do the whole domain. We can't sort of probe individual points. So, there's a reason for having both, right? The other problem that I've got at the bottom there is texture. So I've been speaking to a few people about this sort of problem as the program's been going on. Texture, which is sort of preferred orientations of crystals, give all kinds of problems in terms of strain measurement. So not only there's problems in terms of strain measurement, but it also makes for an anisotropic material, different material properties in different directions. So the texture is this sort of huge headache for this technique. And unfortunately, a lot of printed products have got a lot of texture. So it's a problem that needs to be solved for it to be able to use in that, in that kind of system. All right, and with that, thank you. And any questions? Part of that's happening anyway, because they keep building bigger and bigger sources. And even in the duration of this project, I think we started at JPark, the Japanese neutron source. It started at 150 kilowatts and is now at probably, I don't know what it is right now, but by our last experiment, it was 700-800 kilowatts. So, and the number of neutrons sort of scales with that. So, no, the beam's the same size, it's just more neutrons in it. So that's happening anyway. They're building bigger and bigger sources and they're getting more powerful. The other way that this can be sped up is, it's right at the start of the talk. Whoops. Yeah, I will. Hang on, I'm just going to find a slide. Right back at the start. Yeah. Yeah. Yeah, and that was my point that I was getting back to this picture for. The other issue is that we make a measurement on an edge. We pick an edge that we pick it for reasons like, for example, it's a big edge, or it's sharp, or it's referring to isotropic properties or whatever. Yeah, exactly, and yeah, so we're really only looking at that little tiny set of wavelengths around that, and we threw all those other neutrons away, right? So obviously, there's other ways of speeding this up by looking at the whole pattern as well, because obviously there's information everywhere on that line.
Could you get more neutrons in the band that you're looking at? You mentioned you still on monochromatic.
Yeah, monochromators essentially select. They don't create, so they just throw away everything else.
You're going to have an even more powerful. Yeah,
essentially that's right. I mean, making more neutrons where you want is actually something that happens as well. So most of these are done from or neutrons from a cold source, because you have a spectrum that comes out of the source, and you want the fat part of that spectrum somewhere close to where you're doing your measurement. And it's not seen here because this is a ray, like this is an eye on eye node, but really there's an eye here which has some kind of spectrum as well. And the nice thing is that most of the cold sources, the fat part of the spectrum is around that kind of 3 to 4 angstrom. So yeah, you pick a source that's got temperature for you, kind of thing.
You mentioned the texture problem in,
Yeah.
for example, is it realistic to expect that it's going to be used for actual single industry, or do we have to make a very carefully controlled model of the component?
Yeah, I mean, I think the end goal is to have it just be able to be applied. Yeah, I mean, we're really interested in the texture problem now. That's the next thing that we're kind of working on.
It's kind of stochastic, right? The thing is to do with the distribution of orientation of the
Yeah.
crystal being fine.
Exactly.
Yep. So it becomes kind of stochastic on the way that.
Yeah, I mean,
probability distribution, which you call texture.
There's two versions of it. There's one version where the whole sample has a texture, and that's probably pretty realistic in a lot of cases. And obviously, what that means is that every brag edge has a different shape from a different direction. You'll still see the brag edges at the same places, but every time you look in different directions, it'll have a different height and it'll have different sort of shapes before it. And so it just makes the physical process of fitting something to that curve and getting something consistent hard. And so if you know what that orientation distribution is and you can build it into the model that you're using to kind of fit the edge, then things get easier, right?
And also, especially when it comes to scale approximation, right? Because on the one hand, you've got detector pixels of a certain size, so you can't resolve further than that. But within that, which is small, you want to have crystals in lots of different orientations, so they're measuring the strain in every direction there. Right?
Exactly, yeah.
So there's something kind of not really made clear mathematically that the strain kind of has to be relatively smooth on the scale where you've got lots of crystals that are more or less.
Yes, yeah, as in the size of crystals is way smaller than the beam dimensions.
Right,
Yeah.
and the strain and it's strain averaging over that beam anyway.
Yeah.
So
the other measurement techniques have exactly the same problem. If the size of your gauge volume is getting close to the size of crystals, then everything starts breaking down and you can't do good measurement. So
right.
that's an assumption we're always going to make.
It's kind of it's sort of crystallography meets tomography, isn't it? In a way.
It is. Yeah.
So you've got those two things happening that happen on kind of different length scales.
Yeah.
And you have to be in a sweet spot where you can assume the crystals are small enough to the big.
Yeah, I mean, I would say it.
Nicely distributed in.
I would say in a slightly different way. That is that. Yeah, these things that I've coloured in yellow are representative volumes in the general continuum sense, right? On both texture and on strain.
I mean, like my kind of overview of it is where we kind of think it must be an asymptotic expansion where you've got to be somewhere on that, the ratio of beam size to, there's an approximation in which you've chosen your samples to be in a sweet spot where it's more like to work.
Yeah.
But it's kind of an interpolation between crystallography and tomography.
Yeah, definitely.
And it's just asking to be written down as a kind of asymptotic expansion.
Yep.
A little bit about the reactive processes of every system.
You mean that one?
Yeah. So the idea you kind of
area stress functions are a more general thing than that. So they'll describe any strain field, sorry, any stress field, I should say. I should start calling it a stress field, right? They'll describe any stress. It's a stress that's div is zero. Yeah, that's right. It's defining. It's another way of stating that the stress, the div of stress is zero, right?
Yeah. So it's a version of div equals zero itself, but
yeah. Well, yeah, that's right.
Yeah, div equals zero itself.
Yeah.
In a 2D fraction.
Yeah, that's right. I guess so, yeah. Yeah, I guess that's the way you could see that.
And then to apply L, the existing L,
Yeah, I mean, we never see them, right? But we can imagine that through putting those operators together, that's what we're measuring, right?
and remember, like, so using the LRT, as you explained that really well, like people think you have to get.
No, that's not true. No, that's only if it's compatible. Whoops. Yeah, this is only true if we can define the strain from the gradient of some potential, yes, from some displacement field. If you can't do that, if it's not a compatible field, you can't do that anymore. Yeah, or is it? Yeah, when this is what you can reconstruct, right? You can reconstruct a solenoidal part. And whether the final result is a combination of two things which you can't see one of them, right?
Yeah. But why is that equal to the length divided by L minus L naught?
Because it's an average. You're doing an average. So yeah, you're doing an average. And so essentially this is the normal. This is strain. I mean, you do this for the two dot products. You've essentially picked out the normal component of strain in the direction that you're integrating. So if you integrate up that strain, you've just got a change in length, right? Cool.
What's the sequence strain?
Yeah, and it's interesting you mentioned that because we started, like everybody who started this area, we started in axisymmetric systems. And our approach, I can dig it up and show it to you. Our approach in that was to minimize strain energy. We had a slightly different version where we kind of rewrote it as a yeah. Yeah, I mean, it doesn't have to be complicated. I mean, literally, you can just sum. Yeah, I mean, I guess. Yeah, I mean, essentially, it's stress times strain, right? Or half the stress times strain. Yeah, so that sort of double dot product, if you like, at every point. Yeah.
That's the
Elastic stored energy, which equilibrium is just another statement of that minimum, right? Yeah. Yeah, and we did that with that. That is the way we dealt with axisymmetric systems. It's just that we essentially just reconstruct and find something, and then just go shopping in the null space for the one that minimizes energy, and that worked quite well. Yeah, and never quite worked out how to do that numerically in anything more than axisymmetric, unfortunately. Yeah, I mean, I guess when you say complicated material, I mean, the only way I can see that happening is anisotropic. Yeah, and it may well work like that. Yeah.
Actually, Chris, well, we saw something a bit like this, but in the way you're minimizing the strain energy.
Yeah.
It's like a regularization, so it picks out something effectively in the null space. But it's a physical, it's a physical condition to minimize the energy.
Yeah.
So it's kind of another type of physics. So it's sort of like a two physics book. On one hand, if we can need some measurement, we also want to minimize something.
If I can go on a tangent slightly, when we first started getting into this sort of area, there's these sort of the first papers that sort of came out in this area by a group in Oxford, and they kind of marched through and just solved this problem for simple geometry, so axisymmetric geometry. They just had some methods they used and just solved it, and they got solutions, and they said, well, that was great, job done, and walked away, and then years later, that paper of yours came out.
I must say though, as a matter of how to do interdisciplinary mathematics, I didn't just publish a paper saying they were wrong.
Yeah.
I went to see
Yeah.
Alexander Korzynski and talked it through with him before I published to say that was wrong.
Yeah.
And he immediately got it. As
Yeah.
he said. It's like
But
immediately.
the interesting.
What can we do now?
But it prompted this really interesting question of, well, how did what they do work? How did it actually work then? Because they, just like, I mean, they're sort of physicists, material scientists, we're engineers, we all work the same. We just try it and see if it works, and then we worry about existence and uniqueness afterwards, right?
Right,
but it doesn't.
That's also a good point, isn't it?
Yeah.
There's a sum of two lessons there. So engineering point of view, we did something that seems to work for happy engineers, where go more towards the physics side, and really kind of think, how can we break this? With a really weird strain. And
And then the mathematician tells you all the different ways in which it's broken.
and mathematicians completely characterize all the things.
And so the point was we went down a path trying to do that, trying to understand why what they did worked, and essentially for a while we were trying to do that in terms of maybe they've just minimized the altitude norm without trying, and thinking that the altitude norm might be the same as strain energy, and it's not. There's a distinct difference between them, so we still don't quite understand why what they did worked.
But unless you compare with the ground truth, as you did using a completely independent experiment, the diffraction, then you won't know. And even that's got loads of experimental errors. But
of course.
You could at least catch yourself being wrong now.
Yeah.
I don't know. I think this has a kind of general appeal to all inverse problems. Right? These are roads that people go down in a way.
Yeah. The suck it and see approach.
Yeah, but especially a problem that has a null space.
Yeah.
But maybe some constraints that at least
fix it.
Yeah, fixes at least part of that null space, and maybe it looks like it works, or it does work because there are some hidden constraints. These are quite familiar roads to go down, which is kind of really nicely illustrated by this.
Oh, thank you. Any more questions?
Check if there's any on the chat.
Thank you.